Okay, yeah, so thanks very much for inviting me, and thanks for coming to the talk. This is joint work with Zhuangfei Hu, Xinda Li, Hongyang Zhang, and Shufan Zhang. So let me describe the class of problems that we're going to look at. We're going to look at recovery of a secret from distance queries. So imagine you have a high-dimensional space, for example, n-dimensional Boolean hypercube, and you want to locate some unknown point S. Okay, this S is for secret. And the way you have access to it is through distance queries. So what you get to do is you get to choose queries, Q1, Q2 through Qi, each in the hypercube. You can choose them possibly adaptively or maybe non-adaptively. And what you get are the distances from your queries to the secret. Okay, you get the list of exact distances. And your goal is, given these distances, you want to make a small number of queries to reconstruct this secret. Okay? And this has some applications to word embeddings that I'll mention a bit later in the talk. Okay, so to get some feeling for this problem, let's first look at some simple distance measures, so the Hamming distance. So how many queries do we need to recover a secret S in the n-dimensional Boolean cube with Hamming distance queries? Someone says n. Okay. Any other guesses? More precise statements?
There's 2 to the n answers. So at least
What's that?
n. There's 2 to the n answers, so at least n.
10 minus 1.
Not quite right, but it's close. Yeah. Any other guesses? So the thing is, an answer is a distance, right? And that is log n bits. So actually, n over log n is the right answer here. So you query these queries in the hypercube. You get these distances. A simple lower bound from information theory is that, as I said, each answer is log n bits, but it takes n bits to describe the secret. So you need n over log n queries, even for randomized algorithms. And the constant here has been worked out in the discrete math literature. I think it might be 2, if I'm right, by Erdős and René. And there's an upper bound of order n over log n queries. There are a number of upper bounds. Let me just give you a very simple one based on the probabilistic method. So this is non-adaptive. And the probabilistic method here just works. So you just choose order n over log n random points in the hypercube. And you just do the calculation. So you consider any set T of a subset of coordinates, say of size little t, on which 2 possible secrets S and S prime might differ. So they differ exactly on that set capital T of coordinates. And you just count. So there are n choose T possible sets capital T. And when I fix my set T, then I have 2 to the T values for S restricted to those coordinates, and 2 to the T values of S prime restricted to those coordinates. Now I want my query to, my random query to distinguish whether or not I have S or S prime. Okay, so I want the distance, whatever Hamming distance I get, to distinguish that. And outside of T, S and S prime look the same. Okay, so that doesn't help you with any distinguishing. Inside the set T, just by shifting, you can assume one of the secrets S is all zeros, and the other secret S prime is all ones. And so what do you need for your distance query to distinguish? Well, you need your distance query not to have the same number of zeros and ones on that subset. Okay, and so you're choosing a random point in the hypercube. The chance that it has the same number of zeros and ones on that subset is roughly 1 over root t. So a random query would actually distinguish S and S prime with probability about 1 minus 1 over root t. Okay? And so then you just do a huge union bound over all choices of set T. So sizes little t of capital T. You have 2 to the 2 T choices, n choose T possibilities. And this is the failure probability. I just put 1 over t here, but you can put 1 over root t here. And if you choose n over log n random queries, you can show that this summation is less than 1. So in particular, there exists a set That's not so satisfying that there exists a set of n over log n points that can distinguish any two secrets, because what would the decoding algorithm have to be? I mean, sort of naively, you would look at all pairs of secrets and rule out one of them. But it's nice that it's non-adaptive, and this can be de-randomized and decode to still get order n over log n queries. And the decoding can be done in polynomial time. And there's this really nice work of Bashuti that studies explicit decoding matrices or distinguishing matrices for this problem. It uses some nice Fourier analysis. I'm not going to get into that, but the point here is n over log n is the right answer for Hamming distance. And these ideas were extended in a few works with Fernandez and Yasuda and by Jiang and Polyansky to other natural distance measures, so LP norms and M-estimators. So now you can, we have the LP norm, the LP distance between x and y, just sum of absolute values of the differences of coordinates raised to the p. And we're considering x and y to have integer coordinates between minus k and k. And we can ask the same question, right? So we have some secret that's sitting in this, this n-dimensional box with integer coordinates, and we're making queries and trying to recover the secret. And you can show tight bounds here up to constant factors that the answer is that you need the min of n, which is the dimension of this box, and n log k over log n queries. Okay, and this works for any constant p greater than 0. When p is less than 1, it's not a norm, but it's still a well-defined quantity. So it's interesting that when k is constant, you're getting a savings over the n upper bound. You're getting n over log n. The upper bound is non-adaptive, as you might like, and the lower bound holds even for adaptive algorithms. And in fact, the same lower bound holds even if you just, instead of outputting the actual secret, if you get close to the secret. Okay, so it's really hard actually to approximate the secret in this setting. So even if you ask for a some approximate secret which has LP distance at most k to the 1 minus epsilon times n to the 1 over p, where epsilon is a constant, the same lower bound still holds up to constant factors. And it gets actually much worse if the answers to your distance queries are not exact. So if you instead have 1 plus or minus epsilon approximations as responses to your distance queries, then actually the query complexity blows up exponentially, and you can show you need exponential and epsilon squared k to the p times n queries. And yeah, with the theme of this workshop, this is not just for norms. This analysis applies for a large class of M-estimators. And I'm just using the word M-estimators to describe a generic distance function between two vectors x and y as being a decomposable sum over the coordinates I of some function f of xi minus yi. Okay, we do need some conditions here, some simple conditions. But for a wide class of functions, you can get the same type bounds. One illustrative example is the Huber loss function, if you've seen that. So what this loss function does is it interpolates between the L2 norm and the L1 norm. So near the origin, it's quadratic, so it's x squared over 2. And when x is 1, it becomes linear. So it behaves like the L1 norm. And it's defined in a way so that it's smooth. Anyway, this is a loss function that's studied. We can get type bounds for this with generic theorems here. OK, so what I wanted to stress in this talk is that previous work has mostly focused on decomposable distances. So as I said, you have some distance function, which is a sum over coordinates of some, maybe you can call it a primitive function, f of SIYI, the ith coordinates of the respective vectors. Right, so Hamming distance, we just added up the number of differences across the coordinates. And this problem of recovering a secret, to the best of our knowledge, hadn't really been studied at all for non-decomposable distances. So hopefully I'm not missing some literature, but we didn't see this problem generalized to a lot of the distance measures that I think people care about in this workshop. So yeah, there are a large class of distances you could ask about. Many of these distances are often defined through an implicit alignment. For example, edit distance, as we just heard about, Frechet, which you heard about earlier, dynamic time warping, earth mover distance, etc. You could ask this recovering a secret problem for all of these distance measures. And we know much less about this. So this talk is going to present some initial bounds for these problems, but I think it's going to ask more questions than give answers. And I hope you find some of the questions interesting and can solve them. So here's an outline of what I'll discuss next. So let me just give some bounds for edit distance first. And these are pretty natural bounds. I would say maybe the most technically challenging part of this work that we had was the bounds for dynamic time warping. But I'm not going to get too much into detail there. So let me just start with edit distance, because there are sort of some really glaring open questions here. So here we're going to consider the setting where we have an unknown binary string S of length at most n. Okay, so I do want to stress here that we don't actually know its length. Okay, it's at most n, and that might cause some problems. And it does for the algorithms that I'm going to mention. So we make some queries, Q1 through Qi. We get our edit distance, exact edit distances to the unknown secret S. And the question is, how many queries do we need? So again, this information theoretic lower bound that we had before applies. So n over log n holds here even for adaptive algorithms. Can we get close to that from an algorithmic standpoint? So here's a simple adaptive upper bound. We can first query with the empty string. And the edit distance of our secret to the empty string will give us the length L of this string. So that's one round of adaptivity. And after that, what we can do is we can let T be the number of ones in the secret. This is easy to learn just by querying the all zeros string of the appropriate length. So that gives me the number of ones in S, now that I know the length. And a very simple algorithm is just to query standard unit vectors here. So we can let EI be the ith standard unit vector, which has a 1 in the ith position and zeros elsewhere. Importantly, the length of this vector is L, which we've learned. It's the same as the length of the secret S. We make these queries, and a simple calculation shows that if the ith bit of S, again, this is a binary string that we're looking at in this edit distance question. If the ith bit of S is 1, then the edit distance between S and EI is T minus 1. Right? You've kind of knocked away one of the ones. Right? For the purposes of this argument, it's at most T minus 1. That's all you need. Otherwise, because this follows from making T minus 1 substitutions. Otherwise, the edit distance is at least T. And here, to argue this, if you just made substitutions, then you would need to make T substitutions, because you'd need to, as you're changing your secret S to EI, because you would need to change the ith coordinate of S from a 0 to 1, and then you'd need to change the other coordinates. You'd need to substitute the other coordinates down to 0, so it would be at least T. You could ask what would happen if you were to do insertions and or deletions. So you can handle these as well. If you try to, the point here is S has T1s, and you're trying to transform it to a string that has 1, 1. If you try to and of the same length. So if you try to delete a character, that's great. You might delete one of the ones, so you're making progress towards EI, but you've changed your length. So then you have to insert a character back. And when you do that insertion, no matter what you insert, you're not reducing the number of ones. So you paid 2 to potentially reduce at most 1 1. And so yeah, so it doesn't help to do insertions and deletions, and you can show that this this distance is always at least t. Okay, so you get a gap here, and it's a simple adaptive scheme. You can learn all the coordinates of S one by one, and yeah, but it is adaptive here. Okay, and one of the key ingredients here that we needed was knowing the length of the string. Okay, we have order n queries here, and here's the first open question already. What is the type bound for adaptive algorithms? Okay, so again, this is just in the log factor, but we don't know the answer, right? So yeah.
Do you know anything if you allow only queries of length n, like length n binary vectors?
You mean if for some n that might have nothing to do with the actual length of the secret?
Yeah. Well, it's the upper bound on its length.
So on the next slide, I'll give a non-adaptive upper bound, and maybe that will partially address that. Yeah. Yeah. So this open question is just about this log n factor. We don't know how to resolve this. Yeah. So the hope is there's maybe some kind of probabilistic argument similar to what we had for Hamming distance, but we don't understand the structure of edit distance, or at least I don't understand it. So yeah. So what about non-adaptive queries? So the lower bound of n over log n still holds. And previously, as I said, we used adaptivity to first learn the length of the secret. And what we could do non-adaptively is just try all the n possible lengths, j of the secret, right? So we're promised that the secret has length at most n. We can just guess all of them non-adaptively. And so now we're querying the standard unit vectors for each possible length j. Okay, so I have eij, the I standard unit vector of length j. And I can also query 0 to the j if I want to know the number of ones in each prefix. This is negligible, just order n additional queries. But the real problem is this. Okay, so the number of these is order n squared. Yeah, and so in parallel, non-adaptively, I query the empty string to learn the length so that I can actually do the decoding. So this is all non-adaptive. And I do the decoding using the appropriate queries that I have. But it seems quite wasteful because I threw away all the responses from the other lengths. So yeah, this gives order n squared total non-adaptive queries and leads to maybe a more glaring open question is what is the type bound for non-adaptive algorithms? Okay, so it's between n squared and n over log n. Okay. So one way of getting better non-adaptive algorithms, which is arguably OK for some applications, is although your secret S is binary and length at most n, maybe it's OK if your queries actually come from an extended alphabet. Okay, so your queries need not be binary. And this actually improves things a lot. So if we query the empty string, and we also query n additional strings, which have the form 1 to the I, 2 to the n minus I. 2 is just some arbitrary symbol that's not 0 or 1. So we query these non-adaptive strings, and this is enough. So querying the empty string is going to give you the length L of the secret, as it did before. And after which you can look at the responses to the queries 1 to the I, 2 to the n minus I, for I going from 1 to L. So we, again, just look at a prefix of these responses. That's enough to figure out the answer. And another one of these sort of case analyses, like we did earlier, is that you can compute the edit distance between the secret S and one of these queries, 1 to the I, 2 to the n minus I. And it turns out that it's, well, I have to get, I'm transforming the secret into this. I have to get n minus I 2s. I mean, I don't have any 2s to start with. So there's an n minus I there. And on this prefix of I elements, well, I have some number of 1s, but for all the 0s that I have in my secret, I have to pay that. You can try fiddling around with insertions and deletions, but they don't help here for similar reasons that we talked about before. Okay, so so this is nice because I can gradually learn my secret by learning how many 0s I have on each prefix and build it up and recover my my answer. So this gives order n queries. Really here for edit distance, additional alphabet symbols don't help. Okay, so it doesn't help to have a 2 and a 3. If the input is binary, you just need one symbol that's outside of 0 and 1. And again, so the information theoretic argument here still works. I mean, so you would still get an n over log n lower bound. But there's a log n gap here as well. So if we allow for one extra symbol for non-adaptive algorithms, can we close this order n versus n over log n gap? Let me just mention some applications of non-adaptivity. Like you might be asking, why stress non-adaptivity? So as you all know, that small perturbations in text data are well captured by edit distance in many applications. And one thing you can do is, if you have a string from text data, you might want to map it into Euclidean space, into a vector, so that you can do a bunch of things on it. You can do Euclidean geometry on it. So that's called a word embedding. And one way of doing that here is if we have a sequence of queries, Q1 through QR, that can non-adaptively recover some secret S, say under edit distance, then we can encode our string S as a list of distances, as a vector. Okay, so it'll be a vector where the number of coordinates is equal to the number of queries that we need in our non-adaptive scheme. And it just lists the distances to each of those queries one by one. Okay, these are sometimes called anchors in the learning literature. And this embedding has some nice properties. I'm not going to get into the implications of them, but you can see because this is a correct non-adaptive scheme that we losslessly encode S with this mapping. It also has some nice properties that if you change S by one coordinate, then the L2 norm of this vector doesn't change so much. So it changes by order square root R, where R is the number of coordinates here. Okay, so it has a Lipschitz property, which is also useful in the applications. So I think non-adaptivity is important. Okay, so let me just quickly mention some other results that we have. So for other distance measures, one is Frechet distance. As you guys know, let me just quickly define it to introduce some notation. So let me define the notion of runs and expansion here. So a run is a substring of your string which contains a single repeated character many times. And the number of runs is just the number of runs in your sequence. So if I have this string x, 0, 1, 0, 1, 1, 0, the number of runs is 5, right? 0, 1, 0, those are 3 runs. 1, 1 is a run, 0 is a run. These are 2 expansions. So I took x and I duplicated this 1 twice. So I got x1 bar, and x2 bar was formed by duplicating this 0 twice. Okay, so 2 expansions. which just extend runs in a sequence. And Frechet is looking at the L infinity distance. So yeah, once we have two equal length expansions, we can look at the L infinity distance between them. Now we have binary vectors, so the L infinity distance is going to be 0 or 1. If we make queries that are binary, let me get back to that. Yeah, I guess for this simple example of two expansions, I've drawn them here, and they differ on this one coordinate. So the L infinity distance is 1, the max difference of any coordinate. And the Frechet distance is just the min over all equal length expansions of this L infinity distance. OK, so Frechet distance has some problems in this recovering the secret model, because there are secrets, pairs of secrets that are pairs of secrets that can't be distinguished by any queries. OK, so let me just illustrate that to you. So any binary string S, it can be written in one of two forms. I can write it as a sequence of zeros followed by a sequence of ones, followed by a sequence of zeros, and so on, where the I1, I2, and so on are positive integers. Or I could have started with a 1 and did the same thing. These are just the runs in the sequence. Both, in this case, I'm just doing an expansion of 0, 1, 0, 1, 0, 1, and the other case of 1, 0, 1, 0, 1, 0. And the problem is, for Frechet distance, if S and S prime are two secrets, and they're expansions of the same underlying binary string B, then they cannot actually be distinguished by any query Q. OK, so we, unlike in the edit distance settings that we looked at, we can't actually hope to recover the secret here. Here is kind of a wall of text, but let me read this. So if we consider a matching between our secret S and Q, you can think of Frechet distance as a matching. Then the point is we can match every symbol in the same run in S to the same symbol in Q, right? Because it doesn't change the L infinity distance. And if S and S prime are expansions of the same string B, then we can pair the corresponding runs in S and S prime. And so we can match every symbol in a run in S prime to the symbol in the query Q that's matched by the corresponding run in S. Okay, so actually the two distances will be the same. Okay, so there's actually no way to distinguish between S and S prime with any query here. So it's not sort of particularly interesting, but it just leads to the notion of relaxing this problem from that of recovering the exact sequence, which we provably can't do for Frechet, to recovering an equivalence class of sequences. Okay, so yeah, if X and Y are indistinguishable by any queries, they are in the same equivalence class. Okay, and once you do that, then it's not hard to see that there aren't that many equivalence classes, right? Because I said that all binary strings, they look like 0 some number of times, 1 some number of times, and so on. So there are actually only 2n plus 1 equivalence classes. There's the empty string, that's 1. That's the additive 1. The first character can be 0 or 1. That's 2 choices. And I have some length. I'm just alternating 0, 1. And that's n choices. So there's only 2n plus 1 equivalence classes here. And it's not hard to argue that if you only make binary queries, you're going to get an answer which is 0 if your query is in the same equivalence class as the secret. And you'll get 1 if it's not in the same equivalence class. Okay, if you have different equivalence classes, you have to cross over between 0 and 1 at some point. And that's why you'll get a 1 here. So really that just characterizes the whole problem. It implies that theta inquiries are necessary and sufficient to recover the equivalence class. If you made fewer than that, you might miss the equivalence class you're in. And if you make one query in each class, you will find it. So that's kind of the story for Frechet distance. In the 1 or 2 minutes I have left, let me just tell you a little bit about dynamic time warping. So as you know, dynamic time warping is like Frechet distance. You look at expansions of two strings x and y, but now it's defined as the L1 distance between the minimum L1 distance over all equal length expansions of x and y. And here things do get more interesting. You can again show that there are secrets that cannot be distinguished by binary queries. So here's a pair of example secrets. You can look at them and try to distinguish them. You won't be able to. So the only hope, again, is equivalence class recovery. The characterization of equivalence classes is a little bit more complicated here, but it's related to a problem, the min-1 separated sum, or MSS, studied by Abood, Backers, and Williams. And using connections between MSS and DTW, we can give tight bounds for equivalence class recovery with binary queries. And I would say that maybe something more interesting, though, is that if you extend the alphabet, instead of only having binary queries, if you allow your alphabet to have 2 extra symbols, we have some conditions on these symbols, but here's an instantiation that works, 1/3 and 2/5, and the length is order n instead of exactly n. Then you can actually recover the secret. Not just some equivalence class, you can recover the secret, and the query construction is really just you query the 0 vector. Sorry, you query 0, you query 1, and you query 1/3 to the I. Oh, sorry, yeah, 1/3 to the n minus I, 2/5 to the I. Okay, so if this is A and this is B, then your queries are A to the n minus I, B to the I. I don't have time to say why this works, but some intuition is, in DTW you have a lot of different possible matchings, and by using these particular, some constraints on the alphabet symbols, you're able to reduce the class of matchings that you have to look at and characterize canonical optimal matchings. Yeah, I won't say more about that, but I want to stress that there are a ton of open questions here. So we don't know if you need 2 extra symbols to recover the secret, or just 1 extra symbol. So we get order n queries with 2 extra symbols. This is non-adaptive. If you only allow 1 extra symbol, we can get order n squared queries and still recover the secret. So we don't have to just settle for the equivalence class. But we don't have any lower bounds there. So that's one question. And yeah, let me just say one more thing that another way. So there are many distance functions I didn't mention here. Maybe you're working on Earth mover distance or something else. One way to get initial well, maybe they are trivial, but initial bounds is just to cast them in a coordinate descent framework. So what that means here is you're trying to, you have some secret, you start with some query, and that gives you some initial distance. And then you try to modify your query a little bit by doing some local move. Okay, so like for edit distance, maybe you do an insertion, a deletion, or a substitution, some local move, and try to see if your distance function can go down a little bit. Okay, and your goal is to walk in the space to try to reduce the distance down to 0. And this does work under some general conditions. So I'm just calling this a step operation where it depends on what your distance is, but the hope is that for many distances you can make these sort of local steps and gradually reduce your distance to 0. This is a way of getting some initial bounds. It's not clear which step to take, and for many distances you might need order n steps to try, and you might also need to reduce your distance n times. And so for a number of natural distances, this gives an order n squared bound. And the hope is maybe that could be improved in general. OK, so that's all I'm going to say. We also have some recent work with Mellon Prabhu here on when you have multiple secrets and you want to recover all of them, but each query only tells you the distance to the closest secret. We don't have very good bounds there. And let me just conclude. So here's a summary of all the bounds in the paper. And if you have any questions, I can take them on this. Yeah.
So we are way over time, but given this is the last time, we can still take questions.
Yeah.
So if you use longest common subsequent instead of edit distance, does the bounds change significantly?
Oh, we didn't. Yeah.
But then you don't have substitutions.
Yeah. So just no substitution.
Yeah.
Yeah. Even. Yeah. I'm not sure. And another interesting thing there is if you just change the costs to be different for insertion solutions. I mean, still all of them would have different costs. I don't know the. I think the same gaps. I think it should be qualitatively similar. Yeah. But okay, I'm not sure. Yeah. It's a good question. Yeah.
If you want to approximate the secret, I gave a 1 plus epsilon approximation.
Yeah.
Can you do it better?
So we saw already for Hamming distance, outputting a secret that has some, even very large approximation is quite hard. So I mentioned it
Just by counting.
here. Kind of by counting. Like even if you wanted to output a secret within this distance in LP norm, the same lower bounds would apply. We didn't characterize the approximability for the new distance measures that we studied though, so that might be worthwhile, yeah.
So if you do not use the extra symbol for in the edit distance case, you do not have a lower bound of n squared, right?
That's right. So for non-adaptive, if we just have binary queries, we have n squared as an upper bound and n over log n as a lower bound.
Any other question? Okay, so let's thank David again.